Well, good morning, everyone. I'm delighted to welcome all of us to this week's seminar, uh, Soil Science Seminar. Our speaker today is Johnson Mtama. Uh, I am Johnson's major professor. Johnson is, by the way, a PhD student, as I say, with me. He prior earned a master's degree also with me. Currently he's a PhD student with me on a Michael Couch / Wayne Schultes fellowship. He earned a master's degree with me a few years ago on a USAID Feed the World initiative. And his baccalaureate is from Sokoine University. He grew up in Tanzania. So I'm saying everything really bad today, Johnson. What did I really want to say? Oh, he's a very successful scientist currently with Tanzanian Agricultural Research Institute. And with that, rather than me fumbling around as I'm trying to figure out what I'm trying to say, I'm just going to turn it over to you, Johnson. The floor is yours.
Thank you very much, Dr. Boras, for a wonderful introduction. So today I'm going to talk about the lime requirement for amelioration of soil acidity in Southern Highland Zone of Tanzania. And before I start my talk, I would like to make a short description of my keywords in the talk. And we have soil acidity, which is the measure of hydrogen ion activity in the soil systems. And the soil acidity is expressed in pH scale, 1 to 14, with 1 being extreme acidic conditions in the soils and 14 being extremely alkaline conditions. Why do we care about soil acidity? We care about soil acidity because it drives lots of chemical reactions in the agroecologies, and we need proper plants performance in the agroecologies. And for us to get that, we need to manage the soil acidity into the optimal levels, such that the plants can be able to explore large area in the root zone, to be able to absorb nutrients from the soil systems, but as well as water that are essential for plant growth and development. Yeah, the other keyword is lime buffering capacity. Basically, the measure of amount of calcium carbonate required to raise the soil pH by 1 unit. It's expressed in milligrams of calcium carbonate per kilogram of soil. And the other keyword is the lime buffering capacity, which is essentially the amount of lime required to be applied in a piece of land that is affected by soil acidity, and raise the soil pH to the level that is desired by the target crop in the specific agroecology. Having said that, then we can navigate the talk now. I would like to express my sincere thanks to the members of the program of study, being led by Dr. Boras and the 4 others. They've been very instrumental for helping me form the program of study, as well as constantly advising me in the course of taking the classes during the semesters. So I appreciate very much for their support. Now we can get into the business, talk about the Tanzania. So Tanzania is located in East Africa. Now most people know about East Africa. So in the eastern part of the country, it is bordered by the Indian Ocean, and in the northern part bordered by Kenya, and northwestern part bordered by Uganda, Rwanda, and Burundi. And in the extreme west part of the country, it is bordered by Democratic Republic of Congo. I know maybe people have heard about the Congo forests. So the Congo forests are right on the extreme west of Tanzania. These areas receive a lot of precipitation because of the Congo forests. In the southwest, in the southwest part of the country, we are bordered by Zambia and Malawi. And in the extreme south, we are bordered by Mozambique country. Tanzania is also very rich in terms of some other natural features. We have got Great Lakes. We have Lake Victoria, Lake Tanganyika, and Lake Malawi, also known as Lake Nyasa. But in terms of the farming systems, Tanzania is very diverse, and the farming systems in the country are organized based on the altitude from the sea level. So we have the lowland agroecologies, the midland agroecologies, and the highland agroecologies. In the lowland agroecologies, most of the crops being grown in these areas are the cashew nuts, the paddy, and some horticultural crops such as onions, tomatoes, okras, etc. These areas receive biannual rainfall patterns, and the midland agroecologies are characterized by limited amount of rainfall, always less than 500 millimeters per year, and the crops being grown in these agroecologies are the short-term maize varieties, which can mature within 90 days. But also we have the finger millet being grown in these areas. We have sorghum. So those are types of common crops in the midland agroecologies. Then we have the upland agroecologies, the agroecologies which receive a very high amount of precipitations in a season, and they have the unimodal rain patterns. If the crops being grown in these agroecologies are the late maturity maize varieties, which spend more than 5-6 months in the field. But we have the coffee being produced in these areas, as well as tea. And in the recent years, avocado production is coming up very seriously. So as you can see, the country is very diverse in terms of the farming systems. Tanzania attained her independence in 1961. At that time, it had the population of around 13 million people. But as of now, the country is having the population of around 70 million people. And agriculture is the main business of the occupants of Tanzania, and it contributes around 29% of the GDP. And out of this population, 75% of the people directly involved in agriculture, which means they attain their livelihood through agricultural activities. And 80 to 85% of these populations of these farmers are small-scale farmers who farm between 3 and 5 acres in a season. Tanzania has a land area of around 945,000 square kilometers. That is around like 1/10 of the US size. And out of this land, 44 million hectares are suitable for agriculture. But as of the recent records, only around 10 million hectares are under cultivation. And 28% of this land is being cultivated in the southern highland zone of Tanzania, and contributing to around 35% of corn grain being produced in the country. But much as soil acidic conditions are concerned in the country, we have the around 14.4% of the total land in the country being acidic. And with the review of the acidic data in the southern highland zone, most of the land has the soil pH less than 5 unit. And we have some very few areas, especially the Rift Valley areas where there's lots of paddy production. We have pH records of above 8, but these are very rare spots in the southern highland zone of Tanzania. So right on the left-hand side, you can see this is the record on maize production in the country between 2011 and 2019. So in this time, Tanzania has produced around 6 million tons of maize from the 375 million hectares. If we work out the productivity from the land cultivated and the amount of harvest being attained in this period, we can get very low productivity, around 1.5, as shown in the graph in the right-hand side of my slide. So this sends a very strong message, because this is a very low productivity in the country, as opposed to the potential that we have. We have got serious breeding programs in the country, and we have got so many high-yielding maize varieties which have been released by the breeders in the country. We have got good rainfall patterns, but still the productivity is low. So this makes a call to land use managers, soil scientists, that we really need to come up with something to intensify production in the country in order to feed the growing population of the country. Otherwise, it's going to be a very serious challenge end of the day with this rapid population growth. So the government of Tanzania has been making several efforts to make sure that we transform agricultural sector in the country. So with the government having the Tanzania Development Vision 2025, aiming at transforming low productivity economy to semi-industrial economy, the government has been trying its level to make sure that it creates the enabling environment as much as the police of the country is concerned, the legal frameworks, and several strategies and programs have been implemented in the country, such as Agricultural Sector Development Program 1 and 2. And these programs were created to help the country strengthen the breeding program through the work that is being done by Tanzania Agricultural Research Institutes. So the government has been providing funding to the TARI, or Tanzania Agricultural Research Institutes scientists, and they have been working on the development of these different varieties of different crops, as I have mentioned. Specifically for maize, we have got so many maize varieties being bred and released for use in different agroecologies in the country. As I have mentioned, the kinds of agroecologies available in the country. But these varieties also have received fertilizer recommendations programs that are, again, complying with the agroecological requirements as they distribute in the country, as well as the pest management programs. But also the government has made some extra effort formulating the Southern Agricultural Growth Corridor of Tanzania, whose goal or whose responsibilities is to explore agricultural opportunities in the Southern Highlands Zone by finding out what are the key challenges affecting the farmers in the Southern Highlands Zone, and making those challenges into opportunities to different private stakeholders, such that the farmers can get the solution to their challenges, but then these private sector stakeholders can take them as opportunities to make some profit while helping the farmers resolve the key challenges they are facing. Also, the government of Tanzania has implemented a program called BRN, which stands for Big Results Now. And this is the program that was designed following the post-harvest challenges existing in most of the producing areas in the country, because most of these producing areas are located in the very rural areas. And main challenge was the accessibility of these rural areas, especially during the rain seasons. So to resolve this problem of post-harvest losses, the government came up with a plan to fund the rural roads network constructions, and this has highly catalyzed the agricultural sector development and transformation as of the recent times. But not only the rural roads, also the construction of the warehouses that have been used for storage of the harvest produced from these production areas located in the rural areas until when the markets can be accessible for these produces. So that was the national effort within the national effort, but also we have the regional and global frameworks as part of the efforts or initiative to help transform the agricultural sector in the country. So what the government of Tanzania has done is trying to domesticate all these efforts that have been agreed at the regional and global level, such as comprehensive Africa Agricultural Development Program aiming at enhancing agricultural transformation for livelihood in Africa. So the call for CADI to African administrations is to make sure that they allocate at least 10% of their budget into agricultural sector to catalyze the agricultural transformation, but also make sure that at least they attain the annual growth sector, the annual growth rate of the agricultural sector of 6%. So the African administrations are also looking forward to implement this kind of administration at different levels. So right now, countries are still struggling how best they can implement this kind of agreement, which is led in the region. But also we have the Alliance for Green Revolution for Africa, whose goals are very similar to the goals of CARDIP, and the way this has been implemented is the same way as the Agricultural Sector Development Program 1 and 2. So they work very close with the Agricultural Research Institute, the National Research Centers, as well as the International Research Centers, where the scientists make write-ups to address different challenges affecting the agricultural sector in the country, and those write-ups that are found sound and relevant to the prevailing conditions have been receiving funding from AGRA, and this initiative has really helped Tanzania into the release of so many maize varieties, as well as all those kinds of fertilizer recommendations I've been speaking about, which are suitable for different agroecologies in the country. Also, the domestication of the Sustainable Development Goals, especially goal number 1 and 2, poverty eradication and hunger eradication in the country, those have been domesticated through the implementation of all those programs I've mentioned behind. Then we have the Feed the Future program. This is the US-based arrangement. So the government of the United States is collaborating with the African administration, trying to help address key challenges affecting the African countries in different arenas. So it has helped the capacity building for the national research centers, but as well as the universities. I am one of the beneficiaries of this program, as Dr. Boras mentioned during the introductory remarks. They sponsored my master's program back then in 2013 to 2015. So these kind of collaborations really help Tanzanians transform the agricultural sector. But one remark I need to mention about these kind of collaborations, they are so much affected by the diplomatic relations of the nations, like the way your nation is collaborating or relating to different nations in the world is going to seriously affect different research or programs in the country. So that was the part of it, but then I have the organization of my PhD dissertation components. So I have 5 chapters in the PhD dissertation, but 3 of them are the research chapters, which is chapter 2 about the pedology of the representative agroecologies of Southern Highland Zone of Tanzania, and chapter 3, which is about the absorption of phosphorus in the acidic soils of Southern Highland Zone of Tanzania, as well as the 4th chapter, which is about the amelioration of acidic soils for enhanced corn productivity in agroecologies of Southern Highland Zone of Tanzania. So, and the last one is the general introduction, the general conclusion. So today's talk is going to focus on chapter 4 about the amelioration of acidic soils for the enhanced corn productivity in Southern Highland Zone of Tanzania. And I'm going to talk about just one component in that chapter, which is about liming requirement for the acidic soils of Southern Highland Zone of Tanzania. So the general objective of the study is to establish the site-specific lime requirement of the Southern Highland Zone of Tanzania. And this general objective has been unfolded into 2 specific objectives. One is to compute lime buffering capacity in the Southern Highland Zone of Tanzania, and second, to compute the lime requirement in the Southern Highland Zone of Tanzania. We have 2 hypotheses for this study, one being the sites in the Southern Highland Zone of Tanzania have equal lime buffering capacity and lime requirements, and the alternative hypothesis being the sites of the Southern Highland Zone of Tanzania do not have equal lime buffering capacity and lime requirements. So these are the sites of my experimental work in Tanzania. So this is the location of Tari Uyole, where I'm working, and all my operations start from this point here. So I have got one site at Tari Uyole premise, and then I've got one other site in the western part of the country, which is around 70 kilometers from Tari Uyole headquarters, and the other site is located in Yoringa region, which is around 270 kilometers from Tari Uyole. And the last site is located in Njombe region, around 250 kilometers from Uyole site. So about the site's description, so these sites are very diverse in terms of altitudes, in terms of precipitations, but as well as the kind of the soils we are working with. So we have the Afisols at Mbimba sites, and the Altisols at Igeri and Kifuriro sites, and the Andisols at Uyole sites. So the work was organized into two phases. First phase was the field work, and the second phase was the lab work. So for the field work, I conducted the reconnaissance study into the identified sites, especially the areas delineated for experimental purpose, where I observed the kind of vegetations in these areas, as well as the soil colors, but also looking at the depth by ogling across the delineated area for experimental purpose. Also, we excavated one pedon in each site that was used for the classification of the pedological. But also, having done this reconnaissance, I designed a soil sampling plan, which I later implemented it, where one composite sample in the experimental delineated area was composed of 10 subsamples, and these subsamples were collected in the zigzag way or zigzag fashion to enhance or to maximize the representation of the soils of the area. And these samples were taken to the laboratory, where for the purpose of lime characterizations, we looked at the liming buffering capacity and the lime requirement. These are the other methods that have been used to characterize some other physical of the study sites. The characterization of the lime buffering capacity and the lime requirements, two working solutions were used, that is calcium hydroxide, hydroxyl 0.025 molar and 0.01 molar calcium chlorides. And I determined the soil pH in three different ways. So one is determination of the soil acidity or the soil pH using the soil water ratio, where 20 grams of soil was used and mixed with the 20 mils of water, stirred at 10 minutes interval, and then left to settle for like 10 minutes. Then I read the soil pH to determine the active acidity of the soils in the experimental sites. And this active acidity is really very important for devising the kind of liming intervention in the study sites, because we look at the amount of acidity available on these sites by observing the active acidity, which is a measure of hydrogen ion concentration in the solution. When we have the pH value greater than 5.5, we might consider that liming is not very much important, though there are some studies which show that we still can do liming even to the pH points of 6.5, and you can still get some good results of liming reactions in those soil systems. But then the other method was the determination of soil pH by soil calcium chloride method, where again 20 grams of soil was mixed by 20 mils of calcium chloride and stirred well, left at 10 minutes interval, left to settle for 10 minutes, and then record the soil pH of this kind of solution. And this is the method that is aimed at characterizing the reservoir acidity of the soils. And the reservoir acidity is a very important factor in characterizing soil or in devising lime amelioration intervention in the agroecologies, because this expresses the amount of the exchangeable acidic cations present in the exchange sites. And it's very important to address these exchangeable acidic cations in the exchange sites for us to have an effective lime amelioration programs. Then I determined the soil pH by adding calcium hydroxyl to the solution of soil calcium chloride at the ratio of 1 to 1. I measured 3 mils of calcium hydroxide, added it to the solution of soil calcium chloride, shaked it for 5 minutes, then let it set for 30 minutes to allow the equilibration and the buffering reaction to take place with the calcium hydroxide in the soil systems. Then I recorded the pH after 30 minutes and called that pH 2. After getting all those 3 measurements, then I used this equation, which is adopted from a manual, Dr. Thompson and Frizzy, produced in fall 2022. So lime buffering used times molarity of calcium hydroxyl times 1 consisting of the calcium hydroxyl, calcium chloride in the soil, that is pH 2, recorded at 30 minutes, and then minus the pH of the soil using the calcium chloride method. So with these parameters in place, I was able to compute the lime buffering capacity at 30 minutes. Then the lime requirement was calculated by using this relation, lime buffering capacity obtained from the previous relation I presented about, times the difference between the target pH and the pH at calcium chloride solution. So for this case, for maize, the target pH used was 6.8. So the difference between the 6.8 minus the pH of calcium chloride times the lime buffering capacity gave me the lime requirement in milligrams per kilogram of calcium, milligrams of calcium carbonate per kilogram of soil. So it's very important. This kind of lime computation is very important when it comes to the management of the soil acidic conditions, because as I said, the soil pH is really driving the chemical reactions and the nutrient availability in the agricultural systems. So if you look at this graph here, it is showing the availability of different nutrients in different pH levels. So this is making a call that it is really important for soil scientists or land use managers to manage the soil system into the optimal levels where we can maximize a nutrient uptake by the crops as well as the microbial activity. As we all know, the roles of microbial activities is to convert the organic form of the nutrients into the inorganic forms, which are uptaken by the plants for the plant's growth and development, and eventually giving better yields. So when we can be in a good position to manage our soil acidic into the optimal windows of acidity, we are likely to increase the productivity of our agricultural ecosystems. And given the conditions of Tanzania of the rapid population growth, this makes a serious call to the scientists in Tanzania coming up with good intensification approaches that can really help feed the growing population in Tanzania. Then we characterize this is the results of the active acidity. So this graph is showing the active acidity at the study sites. So we have the less acidity at Uyole site, and then we had some high acidity for the 3 sites, which is Mbimba, Igeli, and Kifulilo. But then we characterize the exchangeable acidity using barium chloride methods, and the results are as depicted in this graph in the right-hand side of my slide here. So we have the highest exchangeable acidity in Mbimba sites, implying that we had lots of exchangeable acidic cations in the exchange sites in the soils of Mbimba. but then we had relative low exchangeable acidity in the other three sites, Igeri, Kifyulilo, and Uyole. However, there's one note for Igeri and Kifyulilo. I'll show it in the next slide. The amount of soil organic carbon in the two sites, Igeri and Kifyulilo, are very high. And this presents a possibility of the complexation of the aluminum ions with the soil organic matter in the area, hence reducing the amount of active exchangeable acidity in those sites. But we also characterize the clay contents as they are presented in this graph here. So then this is the relation I was talking about for soil organic matter. The high soil organic matter in soil organic carbon in two sites, Kifyulilo and Igeri, but for Mbimba and Uyole, the amount of soil organic matter is not as high as the other two sites. Then we have the results in these histograms on the soil pH using different methods, which is basically the expression of active acidity or reservoir acidity, and then the pH after the buffering interventions. So if you look at this the black column here is indicating the active acidity pH in soil water systems. And as I said, this is very important when a scientist or land use managers want to devise the acid amelioration programs in a specific agroecological conditions. When we have high active acidity, it means we really need to devise an intervention that can really help combat that problem. And the best way to design that program is to compute the lime requirement based on the reservoir acidity. So you can see in the second histogram here the amount of acidic level is relative more, and this has been attributed by the exchangeable acidic cations being kicked out of the exchange sites from the soil systems by the addition of calcium hydroxyl. And as they are kicked into the solutions, the hydrolysis of aluminum can really increase the acidic conditions of the systems. But then the other histogram here, the gray one is showing the pH after the interventions of lime buffering reactions. When we added when we added to the soil the calcium hydroxyl, allowed it to equilibrate in 30 minutes, then recorded the pH. You can see the pH somehow increased from the previous pH recorded in the calcium chloride soil system. So this is the same trend for all the sites. As you can see, the extreme case is for Mbimba, and for your site, the situation is more or less optimal for plants performance and microbial activity in these areas. So this is the results for lime buffering capacity. We had the highest lime buffering capacity at Mbimba, where around 1,475 milligrams of calcium carbonate were required for 1 unit in these soil systems of Mbimba. And the other extreme case is for Uyole site where we needed only 331 milligrams of calcium carbonate to raise the soil pH by 1 unit. And for the other sites, Igeri and Kifyulilo, as you see, around 450 and 560 milligrams of calcium carbonate per kilogram of soil. Then for the lime requirements, again, it's the same trend in the lime buffering capacity. Mbimba had the highest lime requirement given the because these amounts are being attributed by the amount and type of clay that is available at these sites. making more exchange sites that have been occupied by acidic cations. So we need more calcium carbonate to kick out these exchangeable. We need more calcium hydroxide to kick more of these exchangeable acidity from the exchange sites and kick them to the solution such that we can neutralize them with the liming materials. And for the other sites, as you can see the list amount required in Uyole because the acidic conditions are not that serious in that site. These are the nice pictures we had, the profile pictures we had. We have the Andic pedon in Uyole sites, and we have this site in Bimba, which is very high in clay content. And then here are my experimental sites being run in Tanzania at different stages. These folks helping me with data collection. I gave them the protocols so they have the key parameter data I need to help me discuss well the effect of lime on corn productivity in these acidic soils of Tanzania. So as a concluding remarks, we are working with soils, different types in the agroecologies of Southern Highland Zone of Tanzania, from afisols, altisols to andisols, and the and the order of soil acidity varied across the sites, with Mbimba being very acidic sites and Uyole being less acidic site. And again, the lime buffering capacity varied across the sites, as we have seen in the results and discussion. And the same for lime buffering capacity. But the most important information we draw from this study is for the Southern Highland Zone of Tanzania productivity to be enhanced, we really need to come up with the specific, site-specific lime requirement to help improve crop productivity and ensure the agroecological health of these soil systems. Because if someone uses the intervention that is required from Bimba site at Uyole sites, it's very likely that we are going to shoot the pH of this Uyole sites. And once we shoot the pH of Uyole sites, we are likely to fall into the problems of other essential nutrients and availability, such as micronutrients like zinc, copper, etc. And again, according to Justus Liebig, that the yield productivity of a soil in an agroecological system is a function of all essential nutrients. Once we have one nutrient limiting, even if we have all other nutrients at the required levels, we really cannot tap the yield potential of a specific genotype or variety in that specific agroecologies, unless we address that limiting nutrient in the soil system. With that being said, thank you very much for your attention. I can take some questions at this point.
Well, thank you, Johnson. Great presentation. Enjoyed that a lot. And of course, he is available for questions. So for everyone online, please ask Johnson questions. So Johnson, I have a question while people are formulating their questions. I have two questions, actually. So, here in the United States, we often think of maize yields, corn yields, and bushels per acre. So when I look at your average yield of maize in Tanzania, in bushels per acre, it's about 25 bushels per acre. Are those hybrid varieties?
Well, so in most cases, these are not the hybrid varieties. Like I said, the dynamics of the farmers in Tanzania is very complex. So
right,
the average yield is really affected by the extremes, because some farmers don't use the hybrid varieties. As a result, they get very low yields.
right.
And when it comes to the computation of the gross maize production in the country and working out the average, the yields become very low. But as I mentioned in my presentation, with these different efforts the government of Tanzania has taken and the collaborations with different international organizations, we really have got some nice hybrids developed and released in Tanzania, whose yield potential are as high as 9 to 10 metric tons per hectare.
Right. So yeah, that's what I was gonna ask a follow-up about is certainly your work with TARI when the farmers are using hybrids and actually following the recommendations like what you are putting together at the Uali station, they're getting 10 metric tons per hectare or so for yield, 9-10. And that's starting to be something like we might even be okay with here in the United States. So this is very good. And then my follow-up question is, so as you think about lime in Tanzania and such, here in Iowa, it's fairly easy to buy ag lime. How common, how costly both is it in Western Tanzania? Are there good sources of lime and are they affordable?
Well, that's a good question, Dr. Boras. But as of now, the dynamics are changing. So of the current situation, the average cost for a 50 kilograms lime material is around 12,000 Tanzanian shillings. This is the price in the like zonal areas of these agroecologies I was talking about. But if somebody is visiting the production area, the cost is around 8,000 Tanzanian shillings. So what the government of Tanzania has done, it has called upon the engagement of the private sector to see how best they can explore and characterize several liming material sources across the country, such that we can have good sources of liming materials closer to the production areas to make these resources available to the farmers at a cheap price. So we anticipate with these liming sources being closer to the farmers, the price can go down as much as 5,000 Tanzanian shillings per 50 kilograms bag.
Right, that'll be essential, you know, for everyone. But yeah, that sounds excellent. So thank you.
Yeah.
So let's see. There's a long question from Dr. Thompson has several questions in the chat. I'm going to read them to you. Is that okay, Johnson? And then you can answer them.
Yeah.
Okay. In the government program for agricultural transformation, does the government encourage farmers to continue to farm, or does it encourage people to move to urban areas to increase industrial capacity?
Well, yeah. So the government of Tanzania is really concerned about the farming systems in the country and the food security. So it's the government is trying to create good enabling environment in the production areas such that the farmers can be satisfied and engage in the farming activities in the rural areas instead of thinking of moving from the rural areas to the urban areas. So as of now, the government is trying to improve the rural roads, the health facilities, supply for electricity, as well as the water sources. So these days, people feel very comfortable staying in the rural areas, engaging in agriculture, because they get almost all the essential services they need that could be attained in the urban areas.
Excellent. Thank you. So I'm changing the order of Dr. Thompson's questions. He has a series of them. They're really nice. What were the various parent materials of your soils? Because you have such a wide range of pH depth profiles and wide range of pH in the A horizons. What were the parent materials of your various soils?
So the parent material for the acidics for the Uyole site is the pumiceous volcanic ash.
Right.
And for the other sites is more or less residuum formed in press, because these are very old soils.
Right. So the Uali site is the pumice from volcanoes. The other sites are various ancient bedrocks.
Yes.
And then for your, since you're working with especially trying to adjust lime rates or adjust pH, Dr. Thompson asked, how thick were the horizons that you sampled, or really how thick are you trying to affect pH? Like here in the US, we often shoot for 15 centimeters. What are you doing for adjusting the pH in with your soils in Tanzania?
Well, thank you for a nice question. And my bad, I did not describe this in my methodology, but my soil sampling depth was 30 centimeters from the top. So that's the common soil sampling depth for corn fields in Tanzania. So I worked in what is common in the country. Yeah.
Mm-hmm. Excellent. And so with that 30 centimeters then, is that the depth of tillage the typical farmer does as well? Or what's the logic behind using a 30 centimeter deep sample?
Well, so that is like the plow layer.
Okay, yeah.
Yeah.
Right. And that's what I thought. So that's very good. Excellent. So are there other questions? I can keep asking. Dr. Thompson has a couple more. I'm happy to ask them, but I want to make sure other people have a chance to ask questions too.
I have a question.
Excellent.
Can you hear me? This
Yes,
is Walter
Walter.
Souza.
Please, yeah.
Johnson, thank you so much. I really enjoyed your talk. I appreciate you talking about home and presenting the diversity of the wonderful things that are there. So I'm really grateful today. So I understand a little bit of soil science to super dangerous. So I saw if you'd go back to your slide where you had 3 histograms of water, pH 1 and pH 2. And maybe this question is also, it's just obvious to you, but to me,
yeah, slide
that
20.
one.
Yep.
So if I look at the magnitudes of the pH 1 and 2 at Mbimba compared to other places, is that indicative of the lime requirement because of that such a small delta, or what is going on there?
So
from
like
pH 1?
Okay, so like I explained in my talk, so we use the pH in water as an indicative. Do we really need the lime intervention in this site or not? Or to make it in the more scientific way, this is a measure of active acidity in the soil. It's the amount of hydrogen ions concentration present in the soil systems. So it just tells you that, hey, there is a serious problem of soil acidity in this condition. But then when we want to devise an effective lime program, we do not use the active acidity. We need to use the reserve acidity because that is the measure of the amount of exchangeable acidic cations available in the exchange sites. And for us to be able to neutralize this acidity, we need to kick out all these acidic cations in the exchange sites into the solutions, such that they can be neutralized by the liming material we are applying in the system. So that's the technical description of the two histograms.
Okay. Thank you.
Well, Johnson, I'm going to ask another one of Dr. Thompson's question. So what statistical test are you using to test the hypotheses, your hypotheses?
Well, so I am not yet there because I expect to use different statistical tests such as ANOVA,
okay,
analysis of variance. Because the design of my experiment is the factorial experiment design. So I'm going to use the ANOVA analysis to test my hypothesis.
So sounds very good for the liming part of it. Yep, excellent. Yeah. Well, sounds very good. Well, I can tell we're running out of time and some people are leaving and such. So I want to thank everyone for listening to Johnson. I want to thank Johnson again for speaking. And yes, thank you very much for clapping. And then I want to invite everyone back next week when we will meet in person and online for Ms. Zhao's seminar on drainage systems impact on nitrous oxide emissions. So I look forward to seeing everyone a week from now if you're available at all. Thank you all very much. And Johnson, thank you again.
Thank you very much, Dr. Boras.